And the last thing that doesn't require anything from you to do. So if you are not curious to read, you can again use it as a kindling for your fireplace. And so it is a couple of pieces of paper that have information related to the subject of the course, but everything we will address verbally. It is only supplemental material which you can glance through if you do not do it. It's like second opinion. So there are summary of the material that we are covering from one of the textbooks. There is a joke that I'm going to verbalize. So prepare to smile, just in case. And last page is your presentation. Yeah. Okay. Well, not completely your presentation, but supplemental material. Okay. Start, set, go. First, please. So here is the place where we are in the course material. Here are the subjects of the presentations. Again, if you dislike some of them, just stop by after the class. We can make some adjustments, covering the same material, but maybe repartitioning if someone is not 100% happy. And who we are and what are we doing? We are trying to predict future of electrons because it is a main part of all molecules, or many of electrons. And you do have three ways to predict future. The third one is the best, solving time-dependent Schrödinger equation based on eigenfunction expansion, right? So if you know initial condition, you can represent time-dependent evolution as a superposition of eigenstates with some phase accumulation. But there is a shortcut, the bridge that connects quantum theory to real life, the observables, is a protocol to compute expectation values, right? Wave function with star, operator of corresponding observable, wave function without star, integrated. Last time, we decided, why don't we pursue, why don't we try to pursue to generate an equation which is much simpler than Schrödinger equation to solve, but which will give the same answer, especially if our goal is to predict some specific observable. If we are not torturing each other with boring theories, but if you want to predict outcome of an experiment. So if you do have a selected observable, we do not need the rest of the quantum information. And this is, we can call it first way to predict future, or it can be alternative way to solve quantum problems. Actually, Schrödinger and Heisenberg, who designed this way, were competitors. They designed quantum theory simultaneously, but they looked from different perspectives. And Schrödinger is just, by some reason, became more popular in textbooks. But they were equal and at the same time. So here this gentleman at his young ages, here is his later ages. And if you read, this is from Wikipedia, if you read this post stamp from his native country, it looks like he's taken the Dandelion and position, momentum. He doesn't want what is more important and predict. So the uncertainty that we covered, how many meetings ago? A couple of meetings ago, originates from this gentleman. Okay, another point of view. We decided to look on electron in free space. Not because it is so important for us as chemists. It's just because we cannot do anything else more complicated because we don't have enough mathematical muscles. But we acted as true scientists. We posed a hypothesis and then tried to prove it right or wrong. We posed the hypothesis that if one squeezes electron to be localized at some position, at some near some vicinity of some area in free space, then, and there are no ions to attract it, there are no walls, there is nothing, no materials, then this electron will expand and take more and more space, right? The width of the wave packet will increase. So we did it through taking Gaussian integrals and a third way of predicting future. We predicted how the wave function and then probability distribution behaves in time. But there were two hypotheses, if you remember our discussion many days ago. First one, that electron should follow Newton's laws in average, and second, that it has some quantum nature and expands. So if I'm not fooling you, or if my teachers are not fooling me, if the quantum theory is correct, then in the limit, if you just look on the position, momentum as expectation values, they are expected to behave the same way as they would in classical mechanics. So the center of this electron distribution, if someone kicks it initially, if it has initial velocity, it should move constantly without changing this velocity, or whatever. Momentum is better word, right? So two features. One, I think it is first Newton's law, right? Like a particle without any forces will move with constant velocity forever. So we should check if this Newton's law is maintained for our poor electron in free space. We can do it by Schrödinger approach, but trust me, it will be more of boring calculations. It's better to avoid it. If you apply this trick that we've covered last time with help of graduate student Levi Lystrom, then we will prove that the center of electron moves without change of velocity with much less effort. So again, our scientific goal for today is to check the hypothesis that center of this probability distribution of electron moves with constant velocity, whatever it was provided at the beginning. If it was zero, okay. If it was not zero, it will keep it. Objections? Questions? Okay. And we do not want to be too abstract. We want just expectation value. Please drop on. It is. We do not have this. Okay. Okay. Final beginning. So, if you are tired and you have a lot of classes after today, you can, after this hour, you can just lean back and relax. I will give you a signal when it will be intense in important material. Now it will be more or less mumbling, showing our place in the overall course. So, do you see this scratches? Okay, so we do have three ways to predict future. First, with evolution operator from past to the future, right? Then we have we can predict future by small time increment delta t, right? Having past here and there and multiplying by Hamiltonian with this delta t, and there is a way to solve the future, to find the future by solving time-dependent Schrödinger equation. Don't concentrate. Relax. Prepare your concentration for the last 15 minutes of the meeting. Relax, relax. I'll share the slides so you even do not need to record anything. So if you do have Hamiltonian and initial condition, it is sufficient to predict future. To solve time-independent equation for eigenstates, for eigenenergies and eigenvalues, with a set of these functions and eigenfunctions and eigenvalues, then you take your initial condition and expand it in the basis of your eigenfunctions. So you find your expansion coefficients, and then you construct your answer as a superposition of eigenfunctions multiplied by a weighting factor which is proportional to one of those expansion coefficients, with each of these terms accumulating phase according to the value of eigenenergy, right? No surprises, we all went through it. And then, why these things are going on? Because we need an observable, which is referred to with symbol A here, but it can stand for anything that we measure in experiment. So we have the wave function which changes with time here and there, and we put operator or an observable here, and then we get just a single line that we can either predict by pen and paper or computerized calculations, or one can measure. Yeah. Now, last time we agreed to make a shortcut. If we need just this trajectory of some observable, why don't we merge the definition of expectation value with time-dependent Schrödinger equation? And this is the last equation from Friday, right? Or I don't know if I assume that it is self-evident, but better here. Now you may record it if it surprises you. So when you see this rectangular brackets of two things, it means it is subtraction of their product in different order. Okay? So HA, ha, ah. Or ah, ha. Good. Commutator means ah, ha. So the time increment of the expectation value of some operator is expectation value of this operator commutation with Hamiltonian. And then it can come into one or maybe couple differential equations that are much easier to solve than this stuff. Okay? We'll probably need to review it later, but there are two approaches. One from Schrödinger, one from Heisenberg. They are equivalent in their background ideas, but if you do some crafts work or if you're repairing something at home, there are different tools for different operations. So they are just different tools that have better benefits for one or another type of a problem. Typically, in oversimplified description of quantum theory, one skips Heisenberg at all. Because for minimal number of problems, like particle in the box, one doesn't need Heisenberg, and it is not very well applicable there. But if you look on the broader range of problems, it can help a lot. So Schrödinger looks for infinite number of degrees of freedom. Heisenberg is good for if there is a finite number. So for Schrödinger, you need to diagonalize matrices of operators. For Heisenberg, you need just to solve differential equations. By now, Heisenberg wins. But if you look for equations to be linear, which is really important for any math problems, then Schrödinger is always linear and Heisenberg is not. And nonlinear equations sometimes become a problem. Therefore, one cannot recommend this medication for all diseases, so to say. keep relaxing. Nothing important yet. And here is the map that we are going to develop through the course, and I'm going to draw it almost each second lecture. So we already got a lot of new material, and it's becoming hard to navigate in it. And even if you have your best intentions to use material from this course for the rest of your life, and you like reading your notes every day, it's too much information to navigate. So we need a map to connect the pieces. And later, right now it is not terribly large amount, but we may start ahead of time and maybe make several axes. Like one axis is method, another axis is systems, where our electron in free space is our simplest model where we can apply our theories. And then we will go to more and more complicated theories approaching the true molecules and materials that we can describe and predict their features. Okay? So slowly wake up. Don't concentrate at your full strength here. Our hypothesis is to check that electron moves along the straight line with the same velocity, right? How to say it in one word? Is there like inertia, or we can just take straight line, straight, same speed at free space. So what would be our operator? Which operator should we look at to look how the center of electron is moving?
Position.
Yeah. Are there objections that it would be simplest thing to look on the position? No objections, right? Okay. A equals x. So if we believe to what Werner Heisenberg suggests us, we need to plug in value of Hamiltonian of electron in free space instead of h, and just letter x instead of a, and then find the commutator. So we have x, and now we need the Hamiltonian. What is the Hamiltonian in free space?
Just kinetic energy.
Yep. So there are no ions to attract electron, nothing exert forces on it, nothing exert potential, so there are no potential energy. So P square over 2m, or you can formulate it on quantum language. Again, nothing new in chemistry. And we want to plug in these two things into Heisenberg equation function and look what happens. I don't know, if I show slides instead of talking and writing, it will be really quick. Maybe then we can depart early. But stop me if I will be too quick. Please, I'm here to serve you, not to scare you. So now wake up. from now on there will be new material that, and you may want to record or try to solve this thing yourself. You can be quicker than that. So we need to find commutation between Hamiltonian of electron in free space. Electron is free with position operator. How do we do it? If you do not, like, if you start from scratch, you do not have any tricks. If you want to act by simple definitions.
Right.
We already, a couple of weeks ago, we practiced to compute the derivative and coordinate operators, right? And the trick, so the operators here can be differential operators, acting on functions. So even if the operator is a standalone operator, we should always keep in mind that there is a function on which it acts. And no one forbids us to write this function explicitly, just for the sake of exercise or for mental sanity. And then, after we perform all operations, we can remove it. So here, we will plug in this function of x. And then we will keep in mind that this commutator acts on this function. And we should always obey rules of differentiation and think of this function at each step. But then, after we get the answer, we can remove it. Okay? So, this red function, and if it is free electron, well, this approach is general, it can be applied to anything. But now we are looking for free electrons, so we have only kinetic energy, right? And kinetic energy is second derivative over position with some factors, acting on this function which depends on position. So, what is commutation? Commutation is aha. It's operator times Hamiltonian minus Hamiltonian times operator. Is minus sign, or ha, ah, if you do not want minus sign. H, A, yes, A, H. So the Hamiltonian is this green stuff. Practice it? Yes. Green Hamiltonian. Right? And the operator is our position, x. So you see, here we swap the order of Hamiltonian and operator of interest, but we do not change the order of a function. Function, if you do not do Hermitian conjugation, it's always on the right. And if you do this exercise in public, or you need to do homework in other course on a similar, you can not writing it at all, and then just impress your peers or whoever is grading. But for understanding what is going on, it's more helpful to write the function. So it was no math by now. We just followed the prescription, but from now on, we need to do a little practice of calculus to perform differentiation. So this operator acts on the product of the operator and the function here. And here, because of the commutation, it acts only on the function. So we can always already guess that these two terms will be not equal and the commutation will be non-zero. So this is the main feature, main trick why we are doing it. Because swapping the order of operators will be not zero if you follow all rules of calculus. Now let's carefully open the bracket. So the plan, well, it is too simple, but let's declare a plan. So let's do first derivative first, second derivative second. Good plan. And then by applying each of the derivatives, we will apply rules of differentiation of a product. Right? Apply to one variable and then to second variable. Where do you wrote? Here. So we have one derivative, another derivative, and here we have x, 5. And for the second part, we do not have, we do not need to apply any rules because derivative is applied to function only. Now, this is product. So first we apply first term, second to second term. And this outer derivative stays intact. dx, here dx over dx times function phi plus x times dx over function phi. And then keep this term. Minus x d2 x squared phi. So what is the derivative of x over x? There is no trap, it's a trivial question.
It's 1.
Yes. So it's 1. So from the first term we are getting phi, the function that we keep in mind. And from second term we just do not change it. X times d phi dx. Now we are going to apply the derivative once again. So for the first term, it will be trivial. We just move this differentiation symbol under the brackets, and when we apply it to the second term, it is going to split on two terms once again, right? Because of the differentiation of a product. So it will be d dx over x times derivative of phi plus x times d2 dx squared times phi. And then we have last term, which is minus x d2 dx squared phi, and we do have first term d phi dx. So, which observations can you make in this notation?
Last two terms cancel out.
Yes, perfect. Thank you. Last two terms cancel out. Any other observations? Is there a similarity between these terms? So we can, they are the same. So you can cancel this one and put just factor 2 in front. Right? So right now it was first undergraduate year exercise in calculus, just taking derivatives. But next minute we will return back to our quantum thinking and try to analyze what does it mean. So I've exercised to type all these equations, but it's something that we already did. Cancel, put factor 2, and there should be the heritage of the Hamiltonian, quantum Hamiltonian. So h bar, mass of electron. So if we are looking back into dt, time derivative of position, it will be I over h bar without minus that comes from Dr. Heisenberg. And then we do have this commutator of Hamiltonian with x, which we just found. This commutator will be minus h bar squared to mass, right? Times 2 times 2 times what? What did you got on last slides?
The position derivative of the wave function.
Yes, dx. And we used to have our auxiliary function, which we are going to remove anyway. So it was only to understand, to follow the differentiation rules. Okay, now let's play a little with factors. Can we cancel something? What should I cancel? Yep. Any breakthrough ideas? What else we can do here? Keep silent, I know you know the answer. So, any ideas how we can benefit, how we can convert this Born equation into very intuitive quantum language? So, remember, for each observable, there is a differential operator. And we do not know much of them. I can recall only one of them by the way. So can we identify, look on this right part of equation and identify, any of quantum operators on the right part? Momentum. Thank you. Next time we will ask you. So, thank you, that's correct. Any objections to this correct answer? No, good. So what is momentum? Quantum definition. The differential equation for the momentum. No, not equation, differential form. Explicit form of differential operator for the momentum. So it's not a quiz, but please try to write it down in your notebooks right now. And then you will check me if I remember it correctly. We need it anyway. So P equals. Everyone is ready? So, what did you get?
Negative I h bar d dx.
H bar d dx. Do we see any similarities between this and that? At least the derivative is the same, right? And factors are not a problem for us. We can multiply and divide by factors in order to bring the right part of equation to this form, right? What should we do? So we may want to multiply and divide by this minus I h bar, right?
You don't even need to do that, do you?
Huh?
So you can just cancel one of the h bars each and then...
Yeah, whatever. I just fear to make an error or forget the sign, so it's better slowly but surely, but you may get the answer quicker. So multiply and divide by I h bar. So now, let me switch that over. This derivative and the factor here can be identified as momentum operator. And the rest of the factors can be played and cancelled, like h bar and second power here can be cancelled. And then we will see that d dt of x plus I h bar here h bar over I m p operator. Should I like making, well, I do not like making errors, but I always do that. So let's be careful with minus sign, right? So there should be minus I h bar here and there. And then we go here. Now we can also cancel h bar. And if we do not have h bar, it means goodbye quantum. It means we are back in the true intuitive world where everything behaves as we expect. It's already a good sign. If you do not have Planck constant, then everything is expected to become simple. So we can also cancel I, and minus can migrate to the front.
The minus should cancel with the one that you had left over, shouldn't it?
Yes. No, wait.
Well, just like from the physics standpoint, it should be positive momentum over mass.
Mm-hmm.
Yeah, because on the one that you're switching, then.
Oh, there was another minus here.
Yeah.
Yes, good. Thank you. Perfect. Yes, I've got it without minus half an hour ago. So we identify momentum operator, we plug it in, and then we get the commutator. And by now we already, there is nothing new compared to what you have in your notes. And by now, here the notes go a little slower. It is not yet plugged into Heisenberg equation of motion. It's only the commutator. But at this time, it is appropriate to remove the auxiliary function, the phi. So we can always remove.
Dimitri?
Yes.
Oh, there's never mind.
Okay. So, what have we done? We did plug in the value of Hamiltonian and our operator of choice instead of H and A, and plug them into Heisenberg equation of motion. Now we got this, that increment, the evolution of the center of the electron, whatever its initial conditions were, is just proportional to expectation value of momentum divided by mass, which is velocity, right? So let's assume that velocity is not changing. You can prove it later. It's, again, lack of time today. But if it is, let's integrate. So if the velocity is not changing, then what do we do with differential equations upon they are constructed? We solve them. How do you solve simple differential equations with no functions involved? We integrate, right? So if you have this dx dt, oh, it's all written. for n, and we can integrate left and right part from initial to final time. And then on the left, we will have expectation value of time t minus expectation value at time 0. And on the left, since the momentum is not changing with time, we will get just the constant times duration of time. And then if we move this part to the right, we see that position of the center of electron, center of distribution of electron, is its initial value plus the linear function. So it linearly changes in time. With a little bit more details, this, now concentrate, even if you do not recording. This is a main part of so-called Ehrenfest theorem, which tells that in the limiting case of Planck constant approaching 0, all quantum results give the same answer as classical theories. So there is a transition from quantum to classical. Okay, here is my favorite slide. Meeting is finished. Looking forward to see you on Wednesday, 11th.